All right, so we have two recordings now. I don't know if they're both recording simultaneously or what's going on here. This is kind of weird. You ever have one of those weird days? So that's what's happening now. Okay. All right. Okay. This is recording. It has recorded. Okay, good. We have a few other. Who's the unknown user down here? You. Who that is? Who are you right here? We don't know. Okay. All right. So this is all working. So what I'm going to do, since we're recording here and the other recording may or may not still be recording, I'm going to, I'm sure this says here. Okay. I'm going to kind of go back to the beginning of this. So let's do this. We haven't gotten too far into it. All right. So we're going to kind of start over. And this is really the important stuff right here. Let's make sure this works. They're working. Yes, it is. Okay. Yes, it is. Good. All right. Stability and global circulations. So we're talking about the stability of the atmosphere. And we're talking about the density of the atmosphere. Is it less dense? And if it is, it's generally warmer. Is it more dense? And generally, it's cooler. It's not quite that simple because you do have to factor in moisture. Moisture has to be factored into whether or not the density is higher or lower, because more moisture in the atmosphere will decrease the density. We get into that in another topic. But then gravity is pulling down. And so we have a thing here known as thermodynamic stability, being a measure of vertical density gradients. Vertical density gradients. So as you go higher into the atmosphere, if you have warm air aloft and cold air at the bottom, well, the cold air wants to fall, the warm air wants to rise, so everybody is fine. There's no problem with that. However, if you have a situation like this, you have dense air, dense cold air above. Here's the cold air up here, and you have warm air down here. Well, the cold air wants to fall, the warm air wants to rise, and so you have all sorts of conflict here. And so you'll have what's known as turning over. In fact, the word trope in troposphere actually means turning over. And so here in the bottom of the atmosphere, we have a lot of turning over, because quite often we will have warm air on the ground, which is warmer than it should be, and so it bubbles up through the atmosphere. And then if you have dense air on the ground and less dense air above, like we showed before, that's generally quiet. All right, so here is a neat little shot of a cloud. It looks like it might be a little man. There's his head, there's his arms, and he's standing up. But actually, you can see anything that you like from clouds. They're kind of fun to look at. So we have cold, dense air. And then on the ground, we have less dense, warm air. And of course, that wants to rise up and bubble up. Now, as you know, the air does cool off with height. We know that. But sometimes it cools off faster than it should. Or it's really, really warm at the ground, and it's just so much warmer than it should be there. And so that'll cause these updrafts. And we talked the other day about this. This is the latent heat of condensation. You remember when we go from vapor to liquid and we condense, that actually releases 2,501 joules of energy per gram of water vapor into the atmosphere. So we release all of that heat, and that will change the lapse rate. So here is a thing called an thermodynamic diagram. A thermodynamic diagram. Let me just write that here. A thermodynamic diagram. And this actually is a graphic representation of equations. In other words, how fast the atmosphere cools off with height. It is called a skew-T. All right, a skew-T log P. The skew-T comes from the temperature line. So here are the temperature lines. So here, for example, is the -10 temperature line right there. and you'll notice that it is skewed at a 45-degree angle to the pressure lines. And that's where we get the word skew, because it is skewed and it's temperature. So we're talking temperature lines. And then we have log P. That's the other part of this thermodynamic diagram. Now, here's pressure over here, and it starts off at about 1,000 millibars. But you'll notice that as you go up, it decreases not linearly, but logarithmically. Now, over here, this is just regular height. There's 10,000, 20,000, 30, 40, and 50,000 feet, and each one is 10,000 feet linearly apart from the one below. But pressure does not decrease linearly. It doesn't go from 1,000 to just 0 at some point. It slowly decreases logarithmically. And so that's where that all comes from. So that's the skew T log P. Now, this shows the lapse rates. Okay, so here is a thing called the dry adiabats. It's called an adiabat because that is the rate at which the temperature cools, not because you're adding or subtracting temperature, but because the pressure and volume is changing, and that is changing the temperature. So this is the rate that the temperature will normally cool off. And here you can see here's height in kilometers, here's pressure, which is going down logarithmically. So as you go up into the atmosphere, you'll notice that it's not linear either. It changes. In other words, down here it's a little bit steeper. Here it's not quite as steep. Those are the dry adiabats. Now, you remember we talked about the latent heat of condensation. So that leads us to the moist adiabats. Now, the moist adiabat is a slower lapse rate, much slower, in fact. As you go higher into the atmosphere, if you follow these moist adiabats, they cool off a lot slower. Why? Because latent heat is being thrown back into the atmosphere when water vapor turns to liquid water. And you can just see it right there. Here are the dry adiabats. They're faster. They cool off quicker. And then the moist adiabats are slower. And that's very important. So what do you do with all this? So if you know, every day, twice a day, in fact, weather balloons go up all across the world at the same time, and they take measurements of the temperature at every different altitude. So let's say we are at some location, and at 700 millibars, which is right there, we know that the temperature just happens to be 5 degrees Celsius. So there's 700 millibars. And so you can plot a point. And that is what this thermodynamic diagram is all about. It plots the vertical temperature profile and the moisture profile and the wind profile of any location in the world. So let's say we're going to start off here with the temperature of 5, and that will be at 700 millibars. Let me clean this out here. So we'll do this. All right, so if you start at that location at 700 millibars, which is about 10,000 feet, and the temperature is +5, and there's no significant moisture or anything in the air, and you just go up vertically until you get to 500 millibars right here, you will notice that you go up along the dry adiabat. And that is how the temperature should fall according to all of the ideal gas laws. So you'll go from +5 to -21, from 700 to 500 millibars. However, if in fact the dew point is also 5 at 700 millibars and you start rising, then the moisture in the atmosphere, the water vapor will condense, and then it will release heat. And so by the time you get up here along the moist adiabats, the temperature will only be -9. So that's a big difference. So if it's dry, that is a 26-degree drop from +5 to -21. But if it is moist, it is only a 14-degree drop from +5 to -9. That's really pretty important. Okay, so that is what happens. That's the difference, whether or not there's moisture or no moisture in the air. So that will also lead to understanding how stable or unstable the atmosphere is. So if you have temperature which is falling very, very quickly like this, you have a very steep lapse rate, that would be called unstable. If the lapse rate, on the other hand, is not fast at all, or perhaps the temperature even rises with height, like there's an inversion, that would be called stable. But most of the time, everything is in between here. It's what is called conditionally unstable, and that is when the temperature goes down somewhere between the dry adiabat and the moist adiabat. And that's conditionally unstable because it depends upon whether or not there's a weather system coming through, or there is a mountain, or the sun is coming up and it's getting hot, or whatever. It's all conditional. So it's not necessarily stable or unstable, it's conditionally unstable. So here is another example. This is the way we kind of figure out the stability and if there are going to be thunderstorms today and how tall they'll be and how strong and all that. So we start off with the temperature at the ground. And in this particular case, it looks like the temperature of this particular day, and this was in April of, I guess, 5 years ago, the temperature was about 30 degrees. So you go up along the dry adiabats, because that's the way the atmosphere should be cooling. And then you take the dew point, which is the measure of moisture in the air. And then there is a dew point lapse rate as well. As we discovered last time, it's about a ½ degree per 1,000 feet, a half dew point degree per 1,000 feet. And so you go vertically with the temperature, and then that dew point, you're taking it up. And then you find a level where they meet, and that's called the lifted condensation level. That's where the base of your cumulus clouds will form. And from there, you assume that the cloud will rise. And then if that's the case, it will not rise along the dry adiabat, because now it's 100% humidity. It will rise along the moist adiabat. And so then you can follow that right up. As you can see here, it's actually moving up warmer than the red line. The red line here, this red line, that is the actual atmospheric environmental temperature. And so as long as the parcel of air is warmer than the environment, it's going to continue to rise because it's going to be less dense. We finally get all the way up to a point where the parcel of air becomes the same as the environmental temperature, and that's called the equilibrium level. So the buoyant parcel will rise until it gets to the equilibrium level. And of course, this is going to be the tops of the thunderstorms, wherever they are. So here's what we did. We started with the temperature and the dew point, which we know at the ground. We discovered where the clouds will form. This whole area here is unstable because the parcel of air is warmer than the environment. And then we get up to the top here, where we finally reach the top of the thunderstorms. And that's the way that works. And this area right here is known as CAPE, which we will get into a little bit later. Pardon me. So here you can see the clouds are billowing up to that equilibrium level, which is usually close to the tropopause. We see the clouds bubble up, and then they can only go so high. They can't just keep rising into outer space, because the stratosphere is an area of stability. Pardon me. All right, so here we have unstable air, and it's rising up into this little area. Those are called overshooting tops. This is the This is the anvil, and that's actually, this is the tropopause right here, tropopause. That is the top of the troposphere. And everything above that is warmer, and so it is more stable. So all of the instability is below the tropopause. Everything into the stratosphere, which is warmer, is stable. So stable air at the tropopause. And again, you can see the overshooting tops. They just have momentum that takes them, and then they'll come back down. You can see some towering cumulus right there, which is probably going to break through briefly and then settle down. Here's a current Bakersfield SQT. This is as of about an hour ago. It shows that there was a little bit of an inversion down here. And that means the temperature is actually going up with height, which is pretty unusual, except it does happen in the morning hours when there's radiational cooling at the ground, and then the ground gets really cold. But here you can see we go all the way up to right about here. This is the tropopause right there. And it looks like it's generally dry, although here you can see the dew point. And the dew point trace is in blue. So right about here, this is where some clouds would be. And indeed, we do have some high clouds. Those clouds would be somewhere between 25 and 30,000 feet. Looks like about 28,000 feet. So this is pretty cool. You can actually tell where the clouds are. And you can also see the winds. This is the wind trace over here. Winds are pretty light on the surface, but they do pick up out of the north, starting at around 5,000 feet. Here's around 15 knots, and then they will back to the west at 30. Here's 50 knots right here. Here's 65 knots up here, right around, looks like 40,000 feet. So you get the whole vertical profile. You got the winds, you got the temperature. You can see where the clouds are by looking at the dew point. So that is what the value the SQT has for us. It actually shows us everything we need to know. And this is as of 16Z. There is a thing called RUC soundings. That's RUC for Rapid Update Cycle soundings, where you can look at forecast SQTs into the future, which are very, very helpful. So here are a few other SQTs. This is from Reno, Nevada. This actually, you'll notice that Reno, Nevada, and this is from, when is this from? Where's the date? Oh, here it is. It's all right. That's the 13th of February of 2000. And you can also see that the base, the bottom of this whole thing is at 850 millibars. They're real close to it. And that's because Reno is about 5,000 feet high. So this actually shows exactly where you are. Like if you were to look at a Denver sounding or something like that, it would be very high. So the temperature was 53, the dew point was 17 at the time. And you can see the winds and the profile there. So very, very detailed. Here, this is Key West, Florida on the same day, and you can see that it was a temperature of 82 and a dew point of 71. And the surface was actually less than was actually more than 1,000, below the 1,000 millibar level. And there was also the potential for some thunderstorms. In fact, this is all Cape right there, and here's the equilibrium level right there, which is pretty high, up above 200 millibars. Here is this is from International Falls, Minnesota, a very cold day. This is all on the same day. The temperature was minus 26 Fahrenheit, dew point minus 32. So you can see, and it was a very cold day there. And the temperature basically was rising most of the sounding because it was so cold. Looks like right about here would be about the tropopause, and then the temperature does in fact remain about the same all the way up. Very interesting sounding there. So the adiabatic process, again, means the temperature changes based upon pressure and volume, not upon additional heat or taking away of heat or anything like that. And I should also add that latent heat of condensation and latent heat of evaporation, that's separate from this. Heat will be added, but again, that's not due to a bonfire or torches or something like that. It's not like you're lighting it. There's not any shortwave energy added. It's all a process of pressure generally, and and in the case of, well, like if you were to pump up like a basketball or a football or something like that, or your tires in your car or your bicycle, you pump it up high enough, you can definitely feel the heat. So here it shows that that as pressure increases this way and volume increases this way, if we start here, let's see, the temperature will, as the pressure increases, we're going from here to here, the pressure increases, the volume actually decreases, and the temperature will increase. So this temperature right here is higher than this temperature right here. That's the adiabatic process, which you can see on any SCU-T. And here's another SCU-T, by the way. So here is a SCU-T, and there are many different ways of looking at them. And this shows some location. Where is this now? This is 37 north and 98 west. So that would be somewhere in the southern plains, probably up around Oklahoma or something. And this shows the lifted condensation level, the LCL, which I mentioned before. It shows the equilibrium level right here. This is the top of the clouds right about there. And then there is one other thing, which I'll just introduce right now. It's called the LFC. That is the level of free convection. Free convection. The level of free convection, the LFC, that is where the parcel of air becomes warmer than the environment. And all of this here becomes CAPE. In fact, there it is. And that area that you see there between the parcel of air, which is rising up, which is warmer than the environment, that and the whole area can be quantified. And it is quantified as a thing called CAPE, which stands for convective available potential energy. And so it's energy. It's basically locked and loaded, ready to rise, that sort of thing. And it's measured in kilograms. So let's see here. There it is. Yeah. So there it is. That is CAPE, which is the convective available potential energy. In this case, it is 1,558 joules of energy per kilogram of air. So the higher that is, or the bigger this area is right here, the greater this number will be. And the greater that number will be, the more likely the air will rise. This is kind of hard to see. So this is Texas right here. There. There's Texas. All right. And this is measuring the joules of energy per kilogram of air. And here's 4,000 down here. So that means that if something comes along to cause the air to go up, it is so unstable that it will rise pretty quickly. 4,000 joules of energy is a lot. And so you can measure that. So here is another, this is the most unstable CAPE. And we have a color code down here. So everything in the purples are like up to 1,000. Everything in the greens are up to 2,500. So this is some pretty unstable air right here, up over the Texas Panhandle, and also down here over the Western Gulf of Mexico. So CAPE is a big deal. So the effects on aviation regarding stability and instability, it increases turbulence. Instability does. There's more turbulence in the atmosphere because it'll be more vertical motion. It increases convection, which means that there will be more shower activity. And it decreases predictability because showers, as you may have learned before, they are spotty. We talked about the symbol for showers. It kind of is like a little, it points right down there. So that in a certain area right here, if we have showers, well, you don't know exactly where they're going to be. They could be there, they could be there, they could be there. So a 20% probability of precipitation from showers means that it's just, one chance out of 5 that there will be showers in any particular spot. It's a whole lot different than a huge shield of precipitation, which is coming across, and here's this whole big shield of rain, and it's just all rain, in which case any particular point, there's probably a 90% chance that there'll be precipitation there. So now we're going to talk about jet streams. Does anybody have any questions about stability or instability? And I do apologize for my coughing. As I mentioned last time, I caught this flu on a flight, and I just hate it when that happens, but I'm getting better, and everything will be fine. So jet streams. Now we're going to talk about jet streams. You have a question from somebody? Or comment? Question or comment? Okay. Let's see here. Are we still working? I think we are. Let's get out of this. Look over here. And we are still on. It is started. Okay, good, good, good. Everything seems to be working. Good. All right, back to what we were talking about here. So, oh, okay, that's kind of cool. All right, so jet streams are important to know because they drive weather systems. And jet streams in the upper atmosphere divide cold air to the north from warm air to the south. And the tighter the thermal gradient, in other words, the sharper the difference between temperature, the colder it is up here and the warmer it is, and this gradient right here, the stronger the winds are going to be. All right, so there you go. If it's very, very cold to the north and very, very warm to the south, expect an extreme jet stream. So we've kind of talked a little bit about Coriolis, and it's in some of the upcoming discussions, and some interesting things that people have to say about Coriolis. Is it real? Is it not real? Is it a force? Is it a fictional force? Is it a fictitious force? Is it just an illusion? What is it? And that's up for you to determine. But anyway, so we have the pressure gradient force. Here's high pressure over here, low pressure over here. And the pressure gradient force will always cause wind to blow from high pressure to low pressure. It's part of what's known as the second law of thermodynamics. And that is that everything decays. That's one corollary to it. We all get older and die. But the other thing is that everything goes from hot to cold, from high pressure to low pressure. Energy does not flow from cold to hot. It always goes the other direction in order to balance out. Heat is always re-radiating out. It doesn't suck energy in. It's always re-radiating out. And high pressure always flows down to low pressure. It's sort of like rivers always flow from higher to lower. So in this case, we have pressure gradient force, which always goes from high pressure to low pressure. Wind never blows from low pressure to high pressure, making the low pressure lower and the high pressure higher. That doesn't happen because everything is always trying to balance. So we have the pressure gradient force. That's what this PGF is right here. But as the motion takes place, there's this thing called Coriolis. And the Coriolis effect or force, whatever you like to call it, always acts 90 degrees to the movement. In fact, let me go ahead and show you this. So here is the Earth. Here's the world right here. You can kind of see it. And let's see, there's North America right there. And the world spins this way, such that if my head was the sun would first rise on the East Coast, and then it would rise on the West Coast, and then it would set on the East Coast and then set on the West Coast. So it goes this way. So if you look down from the North Pole, it goes this way. So is this spinning clockwise or counterclockwise? What do you think? If anybody is still here. Are we going clockwise or counterclockwise?
Clockwise?
This looks like it's going counterclockwise, is it not?
Oh, okay.
Well, what do you think? Well, is it going clockwise or counterclockwise? Think. So it's going, let me come out of here. So it's going this way. It's going this way. So this would be counterclockwise, right? Let's do it again. Counterclockwise. So low pressure systems in the northern hemisphere, they circulate counterclockwise because they're taking on the spin of the world. Now, if you look at it this way, we're going to go now to the southern hemisphere. We're going to keep it going the same way. Now, is it going clockwise or counterclockwise?
Clockwise.
Clockwise, exactly. So low pressure systems in the southern hemisphere take on the spin of the world, and down there it's clockwise. And that is the reason why you have that difference between the northern and southern hemisphere. Nothing has changed. The world is still spinning in the same direction. But the question now is, if you were to start at the North Pole, we're going to continue going counterclockwise like this, the way that the world spins. If you start here and you throw a ball toward the equator and it just goes straight, by the time the ball gets to the equator, it will have looked to you that it will have curved to the right because the world will have spun. It will have moved. You understand that concept? That's what Coriolis is. And then if you're going in the other direction, let's say you're in the southern hemisphere and you throw a ball from the South Pole up toward the equator, from your vantage point, it will look like it's curving to the left because the world is spinning. And by the time that straight ball gets to where your target was, it will look to you as though it had curved to the left. So in the southern hemisphere, Coriolis always acts to the left. In the northern hemisphere, it always acts to the right. The difficult part of, that's the easy part to understand Coriolis. The difficult part is what happens if you start at the equator and you throw the ball to the north. What will it do then? Will it still curve to the right like it's supposed to, or not? Does anybody have any thoughts on that? What would happen if you were? Here, let me do it here. So here's the world, and this is the North Pole, and here's the equator down here, and you're down here, and you're going to throw a ball to the north, and here's 30, 45, and 60 degrees north. What would it do? Would it curve to the right? Or
would it curve to the right?
It would curve to the right, yes. But do you know why? It would
Because
curve
of the Coriolis
to the right.
effect?
Yes, it would curve to the right due to the Coriolis effect because, and this is different from the first way of thinking about it. If you're at the North Pole right here, and you throw a ball this way, the world will spin counterclockwise, and it'll look to you as though the ball is curving. By the time it gets to the location, the world will have spun. So it'll look like the ball is turning. But down here, if you are at the equator, the world is spinning about 1,000 miles per hour from the west to the east. But that's not the case at 30, 45, and 60 degrees north, because the world itself is actually spinning slower. You take the cosine of the latitude, and that would be that. All right, so the cosine of 30 degrees is 0.866. The cosine of 45 degrees is 0.7071, and the cosine of 60 degrees is 500. So just multiply those by 1,000, and it's real easy. So if you start at 1,000 miles per hour and you have that momentum, by the time the ball gets to 45 degrees, the world is only spinning 707 miles per hour from the west to the east, but your ball still is moving at 1,000. And so it will appear that your ball curves to the right. Not because it's doing anything, it's because the world is spinning slower at that latitude. So that is Coriolis coming from the south to the north. That is the hard one that people don't always necessarily just grasp. I hope that helped. Okay, let's see.
I have a question.
Yes.
Okay, so let's say I'm at the South Pole, right? And I throw
You're
the
at the
ball, and I throw the ball really far, and it reaches the North Pole because of the curve, right? Will it do a double curve and cancel each other out and go to its original spot?
Wow. Now that is a question that nobody has ever brought up before. I mean, it's one thing going from the South Pole to the equator, okay, but all the way to the North Pole. Okay, so I suppose it would curve. It would appear to curve to the left as you approach the equator, and then it would appear to curve to the right, north of the equator, until it got to the North Pole, and would probably end up at the same spot. That's a very interesting question. Who asked that question, by the way?
Me, Ivan Coreno. I
Oh,
figured that's what it would do, but I was just kind of curious if it was like if it would make that S shape. I thought it would do that, but
yeah, that's kind of cool. All right, so but what we were actually coming up to here, the pressure gradient force and the Coriolis, eventually will get to a point where there's a balance. And so we have a balance between the pressure gradient force, which is pulling, in this case, toward the low pressure system, and the Coriolis, which goes in this direction, and we have this nice balance right here. So that whenever you look at weather maps, you'll find that here's like the pressure, and the winds will be pretty much right along that. The winds will look like they're right parallel to the pressure lines. And that's kind of the neat thing there, because there's a balance between pressure gradient force and Coriolis. Now there's an interesting thing here, because of the balance of the pressure gradient force and Coriolis. There you also have to take into effect centrifugal force. So if there's a low pressure system here and you have there's a trough of low pressure, centrifugal force adds to the Coriolis, so that what happens is that the winds will actually pick up a little bit. I'm sorry, they will actually decrease. The real wind will decrease in a low pressure system because the Coriolis effect is somewhat minimized by the centrifugal force. However, if you have a ridge of high pressure, here's a ridge, what happens here is that the real wind will actually pick up because the centrifugal force opposes Coriolis. So centrifugal force adds to Coriolis in a trough. Centrifugal force opposes Coriolis in a ridge. And that will cause the winds in the low. And this is somewhat counterintuitive, because you might think low pressure system, bad weather, but actually because the centrifugal force adds to Coriolis, it actually will reduce the winds in a trough, but increase the winds over here in a ridge of high pressure. Here is a look at a typical 500 millibar map. By the way, 500 millibars is about halfway up through the atmosphere. Sometimes you'll see this HPA up here, which is hectopascal, which is just another pressure measurement. Pascals is a pressure measurement. And so that's just another way of talking about pressure, but it means the same thing. We have the westerlies, which come here. Okay, so we're going to talk quickly about the horse latitudes. Here's 30 degrees north. We've, I think, talked about the Hadley cells, the Ferrel cells, and the polar cells. Polar up here. And this is due to the upward motion, all of the heat right around the equator. There's so much heat there that it causes a lot of unstable air, and we get all the way up to the tropical tropopause here, and then it comes up to about 30 degrees, and then it begins to sink down again. And so we have high pressure, high pressure, high pressure here. And then that return flow will go both to the south and to the north, and from there, and then it'll rise again here right around 60 degrees north. And this is called the Ferrel cell. So we have the Hadley cell, which is the original one, the Ferrel cell, which is the middle one, and then we have low pressure system up here at 60 degrees north. This is 60, this is 30, and this is 0. And they have the same thing in the southern hemisphere, but the winds are curved because of Coriolis, and so the southwesterly wind really becomes the westerly winds here, and down to the south over the trade winds, we have a kind of a northeasterly wind there. The horse latitudes are called that because there was significant high pressure, and if you're in the doldrums of a high pressure system, and you're a sailing ship trying to get to the New World, you just end up stuck there until weeks could go by, months maybe. And so it was very difficult for people to live. So they either ate the horses or they threw them overboard. And there were a lot of dead horses at 30 degrees north. And that was called the horse latitudes. So the westerlies are there. This is within the Ferrel cell. And this is where all of our mid-latitude weather comes from. And then those horse latitudes and trade winds down to the south. They were called trade winds because these were the winds for Europeans and explorers to get to the New World and with their ships. And then they could go a little bit farther up here to the north and get back to the old world on westerly winds if they were far enough to the north. It would be very difficult for them to find their way back at low latitudes to their home in Europe. So all of the westerlies, that's where we have all sorts of weather with low pressure systems and occlusions and all the weather that we talk about. Fronts, for example, which is a delineation between different types of air masses. We have colder, denser air masses to the north and less dense air masses to the south with more moisture. So here are fronts and and all sorts of what are known as synoptic weather features, which we will talk about in detail in the next class. So the boundary between two different air masses is called a front. And the front is, of course, 3D, and you can see here, it looks like a wedge coming down. The wedge on a cold front is like 30 degrees. So it's a pretty impressive wedge, and it'll move right along, and it'll kind of cause the warm air to ride up over the top of the colder air, because the colder air is heavier, denser. It kind of sticks to the ground. The warmer, less dense air rides up right over the top of it. So we have this wedge, which moves on through it. A warm front is got maybe a 10-degree angle here. It's a much more delicate angle. And so the warm air just rides right up over the top of the cool air. But at any point here into the cold air on the ground, the warm air is not that far above you because of the shallow angle of the frontal boundary. And then we have the occluded front, which basically takes the warm air sector and throws it up above the ground. So there is no warm air in contact with the ground. Here you have generally cool air over here and colder air over here. There are several different types of occlusions where you could have perhaps cold air out front and cooler air behind, and the front looks a little bit different. But in all cases, it is warmer air that is pulled up. And I should say one more thing. An occluded front really is not so much about the front as it is about the low pressure system. When the low pressure system becomes fully mature, that is when the warm air is taken up off the ground, and so it becomes occluded. So the occlusion is really about the low pressure system. This is what an occlusion looks like right here. There is the front and the occlusion right there, which has both the warm frontal and the cold frontal pips on it. But it's all about the low. The low has become very intense at that point. Going to briefly talk about some local winds, sea breezes, and land breezes as well. They're pretty much the same. So what happens is right along a coast, which is pretty important boundary between land and ocean. Since the ocean and the land, they change temperature very differently. It will change dramatically during the day, because during the day the warm air will develop rather quickly over the land, because the land warms faster, and so that'll cause low pressure. And then we have this rising air, and then all of a sudden there's a low pressure system there, so we have to fill it in, generally from the ocean, and that's called a sea breeze. Sea breezes happen in the afternoon, and these local winds are called based on where the wind is blowing from. So if it's blowing from the ocean, it's called a sea breeze. If at night things turn around, let's see if I have that here. Yeah, at night, it's just the opposite. So now the land cools off, and all of a sudden it's cooler over here. And the relatively warmer sea causes warmer air to rise there. Then we have just the opposite. And so now the wind will be blowing from the land, so it's then called a land breeze. And that also happens with mountains and valleys. So here, once again, it's a local wind, and it happens during the day and during the night. Sea breezes happen during the afternoon, land breezes at night. And those land breezes at night can sometimes cause thunderstorms to develop just off the coast of places like Florida and Texas and Louisiana and the Carolinas as well. Scales of analysis is an interesting thing to ponder here. So here we have all these different things that can take place in the atmosphere. And let's look at them here. So we're looking at the scale. So turbulence right here, that would be talking about just feet. That's the scope, the spatial scope. And we're talking seconds to minutes. So not a whole lot of, it's very, very micro. That would be a micro scale. Mesoscale is something that takes place in the tens of miles, maybe 10 to 60 to maybe 100 miles, and taking place over minutes to hours, something like that. Things like tornadoes and thunderstorms, that would be considered mesoscale. And then macro scale, which is really it's micro, meso, and macro. But instead of macro, we're going to call it synoptic scale. Synoptic is just another word for large scale. And synoptic means basically the headline is like a synopsis of a book. You know, it's just give me just the headlines. So generally, it's not as detailed, but it shows large patterns. So we're talking about things that are big, like tropical cyclones, planetary waves, the climate variation, seasonal cycles, stuff like that, taking place over thousands of miles, over years or hundreds of years, perhaps. So that is the micro, meso, and synoptic scale of analysis. As it turns out, mesoscale is probably about the best. Now, first of all, here's synoptic scale. It shows big low pressure systems, and here you can see the analysis over Northern Europe here. But mesoscale is best because it shows detail that you want without going into crazy detail that would be too time consuming. Like if you were to look at something micro scale, you wouldn't want that. But yet it's not macro scale. You get a little bit more detail. So mesoscale is the way to go. And so here is some mesoscale analysis that is available at any time from the Storm Prediction Center. And here's an analysis. This is pressure and wind. Here is a look at moisture and the moisture levels. This is dew points, basically. Here is a thing called precipitable water. Now, this is looking at a skew T. So let's say we have a skew T here, and here is the temperature line, and here is the dew point line over here. This only takes the dew point line into account. Forget the temperature, forget the winds, forget everything. Just look at the dew point, and then that'll tell you how much moisture is in the atmosphere. And you can see areas of moisture plumes, moisture axes. You can see where the dry area is and all that. So that is mesoscale analysis of moisture. Here's the 500 millibar map. And on this, we have not only the 500 millibar heights, but we also have winds, and we also have temperature. There's minus 13, minus 12. Here's minus 16 and 17. So you can see where the temperature is on a mesoscale analysis. Here we have something from up in the atmosphere high. This is 300 millibars. That's up about 30,000 feet. And the 30,000 foot analysis here, in this case, not only does it show the heights and the winds, but what you're seeing here in purple, this is called divergence. And that is where the upper level winds are pulling apart one way or another, and they would be causing a vacuum. And it would be areas where there would be likelihood for upward motion. Here is a supercell composite parameter, and this is also mesoscale analysis. And here, of course, is just a mesoscale analysis of just temperature, dew point, winds, just a regular plots of weather all across. So mesoscale is the way to go. And here's a radar, which is considered mesoscale. So mesoscale in severe storm forecasting is important too. We can look at capes. We can look at the lifted index. We can look at temperatures. Here's a rather complicated, this is a very, in fact, where are we here? This is Texas again. Here's Texas here. But this also shows, there we go. This shows a lot of things. It shows temperature, it shows moisture. It's really pretty convoluted here. It shows dew points, shows sea level pressure. Sometimes it can get really complicated. Other times not as complicated. Here, this is just a large hail threat, but it's mesoscale analysis. This is from the Severe Storm Center. Looking at radar, we're looking at radar right now, and we'll get into this when we get into the 300 course, but this is reflectivity. It shows reflectivity of where the heaviest precipitation is falling. Here we have a thing called this is Doppler, that's the storm relative motion. And this thing is called a couplet right here, which we'll get into in later classes. It shows where precipitation is moving quickly away from the radar, right next to where it's moving quickly toward the radar. And there's most likely a tornado right there. Here you can see motion in the precipitation echoes, and that also is kind of considered a mesoscale feature, showing where precipitation is moving, in this case across Lake Michigan into Michigan itself. And of course, here is just a regular reflectivity. It shows a kind of a hook echo right here. And this is the Bridge Creek tornado from a number of years ago. Here is a neat little shot. This is satellite imagery, and it also can be considered either synoptic scale or mesoscale. Here, this is getting pretty close. This is Hurricane Irma. You can see the eye of the hurricane as it passes through just to the north of Puerto Rico. You can see interesting little features inside the eye. And of course, during severe storm outbreaks, you can see cloud streets right here. You can see, of course, the thunderstorm outbreak across the Red River Valley into parts of Oklahoma, and here too. So this is also considered mesoscale. All right, so we talked about stability and global circulations, and great. So now your assignment is to read chapters 10 and 24 and 25 of the FAA Weather Handbook, and take a look at the videos that came along with the syllabus that I sent on atmospheric buoyancy and energy balance. And next time we will talk about synoptic weather and things like fronts and weather types and things like that. So are there any questions from anybody about anything we talked about? And again, my apologies that there was a little bit of a problem with the correct codes to get on. And this will, of course, be posted. No questions from anybody? Yes.
Okay, so I have one question. I might be just a little confused. The Coriolis effect happens because of the gravity, right? Like just the rotation of the Earth, just because.
Yes.
We're
Did you
spinning
say
around the sun.
Did you say gravity?
Yeah.
No. Coriolis really has nothing to do with gravity.
Okay. So then, what causes the Coriolis effect? Like I know it's the rotation of the Earth, but like the rotation of the Earth happens.
I'll just tell you. So the Coriolis effect is really just an illusion. It is caused by movement in two separate Cartesian coordinate systems. So there's the universal system, which is like outer space, and then there's the system which is moving on the Earth. And so that is what actually causes the appearance of things moving. The world is spinning like we showed you before. You know, if you were at the North Pole and you threw the ball that you're throwing is in the universal Cartesian coordinate system. However, the world is moving. It's in its own little Cartesian coordinate system, which is different. It is relative to the ball. And so from your vantage point, it appears that the ball is curving, not because it's actually curving, it's going straight, but because the reference point, the world, is spinning. And so you can either throw it from the North Pole to the south, to the equator, or you can start in the southern latitudes and throw it to the north. In either case, in that case, you're talking about the momentum that you start with. So at the North Pole, the momentum that you start with is 0. And then as the ball gets farther to the south, the world is spinning faster and faster. And so that causes the ball to look to be in a different spot, even though it's going straight. But it's not going straight in regards to the world, because the world is spinning. If you start at a lower latitude, let's say Bakersfield, and you're going to throw the ball to the north to Vancouver, Canada or something, you start off with the momentum, the west to east momentum of Bakersfield, whatever it is. And so we're around 30, so that would be about 850 miles per hour, west to east. And then once the ball gets to where Vancouver is, Vancouver, the world is not spinning as fast as we are here. They're slower up there, just because even though it's a solid sphere, you know, it's spinning slower until you get to the North Pole where it's not spinning at all. And so whatever that difference is between the west to east flow in Vancouver from the west to east flow, or movement, I should say, here in Bakersfield. That's the difference. It'll make the ball look like it's moved to the right. It has nothing to do with gravity. Does that make sense?
What is causing the world to spin though? Like the
I'm sorry, say again.
what is causing the world to spin?
What is causing the world to spin? Okay,
Yeah.
well, that goes primordially way back to the beginning of things. So the entire solar system is spinning pretty much in the
Right.
same direction. So it all started spinning at the beginning. So the sun is spinning as well. Now, the sun, by the way, is plasma, and it does not actually spin like a solid sphere. So it has so different latitudes actually do spin different speeds, but everything is spinning counterclockwise if you look at it from above. So all of the planets are spinning in that way, and they're all spinning. Everything's spinning. In fact, our solar system is spinning in accordance with the galaxy, which is spinning. Everything is spinning. So
Okay,
what?
and that's spin. But at least from my like logic, from I don't know, my science could be wrong. It is just this is like way back science that I'm trying to remember. But like the world is spinning because it's spinning around the sun, you know, and it's the sun's gravity that is causing the Earth to spin.
Um, gravity. Gravity is is based upon the mass of something. In fact, you know, an interesting thing is that the more gravity there is, time flows slower. In fact, right now we're going to be going to the moon in a couple of years, and there's a big push to come up with uh, a new universal time for the moon. It's called coordinated lunar time, based on the fact that the gravity on the moon is 1/7 that of the Earth, which is interesting. I was thinking about this the other day because what is the gravity in the sun? So if the gravity in the sun is tremendous compared to the Earth, and so time flows so much slower in the sun. You wonder how is it that the stars last for billions of years? Well, time is just barely moving in each one of those. But as far as the cause of spinning uh, related to gravity, I'd have to think about that. You know, I'm not sure. Does anybody have any thoughts on that? Nobody has any thoughts on that. The fact is that the world is spinning at 2.72 times 10 to the 7th radians per second. Actually, it's 2.929 times 10 to the minus fifth. That's what it is. Just off the top of my head, that is the rate of spin of the world, and it doesn't change much. Actually, it does change a little bit based upon whether or not the Earth is warmer or colder. If it is warmer, then the oceans actually expand a little bit, and if there's expansion, that causes it's sort of like if you are a ballerina or if you are an ice skater and you are twirling or you're perhaps on a tube in the river, you know, and if you extend your arms, then you go slower because of the radius of your spin. If you pull it in like that, then due to the conservation of momentum, you will spin faster. So if the Earth gets warmer, it will actually slow down and time will actually be affected. It's just very, very slight. That was an interesting conversation. Does anybody want to opine on anything? This is good.
Okay, to add on to that, right? Because you mentioned the moon, that's the reason why the moon spins or rotates around us because of our gravitational force. And isn't that why like our oceans move because of like the moon's gravitational force? I don't know. And then we spin around the sun because of its gravitational force.
That's true, but the interesting thing is that if you look from above onto the solar system, everything is spinning in the same direction. It's all counterclockwise. The moon spins around the Earth counterclockwise when looked from above. You know, we're all kind of spinning the same way. It all started in one grand motion, and if you go all the way to the galaxy, we're all going in the same direction as well. There are some eccentricities. There are some moons that have been perhaps former asteroids that have been caught, and they might be in a counter orbit around some planets, like I think that's the case with Jupiter and Saturn. There are a few weird ones. And Uranus, it has an axis which is 98 degrees. You know, our axis is about 23 degrees, and that gives us the seasons, but still we are counterclockwise. The Uranus is 98 degrees, and so its seasons are extreme and last for a long, long time. But yeah, the lunar orbit is very important because it does stabilize a lot of things in the world, and it does dictate our tides. You're right. And the interesting thing about the lunar orbit is that it isn't the same. It has a low point and a high point, a perigee and an apogee. And so sometimes the low point is lower. It's not, the low points and the high points are not the same every month. In fact, I did a whole paper on this back in 1995, kind of explaining what might cause the El Nino effect. The El Nino effect, which you probably know is warming water in the equatorial Pacific off of South America, comes with a certain periodicity. But I opined at the time that it had to do with changes in the lunar orbit, and because when the moon is closest to the Earth in its orbit, particularly close, and this happens from time to time, then it has to travel faster in its orbit, because the closer the moon is to the Earth, the faster it travels in its orbit. The farther away it is, the slower. That's Newtonian physics. And so when it's traveling faster, that means that the tides are traveling faster. If the tides are traveling faster, changing faster, that has an effect on upwelling. It was rather complicated, but I think I came up with something. This was like 30 years ago now, 30 years ago, almost. I called it the mu effect. Had nothing to do with museo. It was a mu for the moon. So yeah, interesting stuff. But yeah, what gravity has to do with it? Just the spinning. I don't know. It just all is spinning in the same direction. All the way up to the galaxy, and perhaps even the sub-galaxy. There might be galaxy groups and families that are all spinning in the same direction. All right, any other questions?
I just got one thing on that.
Okay.
Ivan, so the orbit of our Earth, that's affected by the sun. However, the rotation, what is believed to cause that was solar wind, something blowing up, rotating everything in the universe that one direction. That's why everything rotates. It has nothing to do with the gravity or the orbit. It's all from starting motion at one point, and that motion doesn't stop because there is no drag in space.
Got it. That makes a lot more sense.
So you're talking about the Big Bang?
Not the Big Bang. It could be that, but who you talk to says that might not exist. But solar winds are what's believed to have started this perpetual motion, and there's nothing in space to really drag it except for meteors or stuff like that hitting the Earth and major impacts. That's why we can't see like variations in Earth's rotation with different types of impacts.
All right, so let's look at the solar wind real quick. So here is the solar wind, right? Let's see, here it is here. So right here. So there is the solar wind. This is a coronagraph, and you can see no major coronal mass ejections right now, but we do have, this is the solar wind, and the solar wind does vary It's not always the same. Let's get out of here. And let's see. Oh, can I find it here? Oh, let's see. Where is it? Well, let's see here. Solar wind. I was looking for something here that actually gives the current solar wind speed. Maybe this is it here. Let's see. I don't really have it here. Oh, this is interesting. This shows everything spinning. Speaking of spinning, so there it is. You can see here is a coronal mass ejection, and it looks like it is going to maybe hit the Earth. Right, yeah, you can see where it hits the Earth right there. But everything is spinning. Even the solar wind is spinning. So there's just a lot of spinning going on. Lots of spinning. Okay. Hey, this has been a great conversation today. I want to thank both Ivan and Chris for weighing in on all this. So thank you for that. Okay, and if there's nothing else, we will talk about synoptic weather features next time. So thanks, everybody, and have a great day. We'll talk to you later.
Hey, sir, can you hear me?
Yes.
So moving forward, is this the same code that we will use for the duration of these meets?
And who is this now?
Austin?
Oh, this is Austin Art. Okay, great. Great. Yes. Okay. All right. Yes. Yeah, this is the one. There was a little bit of confusion, obviously. There were two of them, and this is the code that we'll use from here on. All right?
Awesome. Thank you.
Thanks, Austin. All right. Bye.